Hello class, we're back with part 2 of section 8.1. We're going to start on page 52 and we'll just do this page for this video since there's a lot of stuff to do here. So the first thing we're going to do is talk about this theorem here, and I want to highlight it because it's actually very important, and we'll come to its utility in just a second. But what it says is essentially that if a sequence, when you take the absolute value of it, limits to 0, then the sequence itself must go to 0. So this is the only time something like this will happen. If the absolute value of a sequence went to 1, it does not mean that the original sequence goes to 1. Only when you do the absolute value and the limit of that is 0 does this theorem hold. And so we're going to see the use of that in a couple later exercises in a few minutes. But for now, just keep that on the back burner. And like I say, the caution here is that the absolute values have to limit to 0 for this to work, not any other number. Okay, but what we're going to do is we're going to use Calc 1 methods to compute the limits that we can. So I feel like we've seen this one quite a bit, but we notice that it's infinity over infinity. And so by L'Hopital's rule, we're just going to treat this like the variable x, right? And so we just get the limit n goes to infinity. L'Hopital's rule says do the individual derivatives. Well, that's just 1, right? Okay, so we've seen that many times before. Now this one, go ahead and try it on your own. This is infinity over infinity. So by L'Hopital's rule, well, just do the individual derivative. So we get 1 over n over 1. And as n becomes very large, 1 over n gets close to 0, and 0 over 1 is just 0. Right? Okay, now for number 3 in this example, we're going to ask, does the sequence minus 1 to the n converge or diverge? Well, I have a picture over here for you. So when n is 1, you get minus 1 to the first, which is minus 1. When n is 2, you get minus 1 squared, which is positive 1. Minus 1 cubed is minus 1. Minus 1 to the fourth is 1, and so on and so forth. And so to see if a sequence converges, or to determine if a sequence converges, you need to ask yourself, do these dots that I've drawn settle down at any single point? And I think you can see that the answer is no. It's just going to keep bouncing back and forth between minus 1 and 1. And so what we're going to conclude is that this is a divergent sequence. And if you like, you can make a remark to yourself that the points don't settle down, right? They don't settle to one location. All right, moving on to number 4, we're going to compute the limit as n goes to infinity of n cubed over n plus 1. Well, once again, this is infinity over infinity, right? So by L'Hopital's rule, this is limit n goes to infinity, 3n squared over 1. And as n becomes very large, you get large numbers on the numerator divided by 1. Well, those are large numbers, right? So infinite. And so this is a divergent sequence. If you were to draw these dots, they would keep going up and up and up and up and up as you went on to the right. All right, these next two we can't do using conventional means, so we're going to have to apply this, this theorem here that I've highlighted. But here's why you can't do it with conventional means. Like I talked about in the last video, there is no derivative, or at least a meaningful derivative of like minus 1 to the number x, right? At least not in the real numbers. Like there's not really a way we can do that. And so what we have to do instead is, let's look at a picture first. So when n is 1, I get minus 1 divided by 2 times the square root of 1. Well, that's just 2 on the bottom. So I get minus 1/2, right? And so that's this point here. When n is 2, I get a negative 1 squared, which is a positive 1, over 2 root 2, which I've drawn right there roughly. The next one, I get negative 1 over 2 root 3, since minus 1 cubed is negative 1. And so that's where I've drawn it there. I didn't mark it as that, but it's minus 1 over 2 root 3. The next point I'll draw is a positive 1 divided by 2 root 4. Well, 2 times the square root of 4 is just 4. It's 2 times 2. So that's this point here. And so you can see that even though these points are bouncing back and forth, they seem to be settling down, right? If you went off to the right a little bit farther here, you would be drawing -1 over 2 root 5, which is just a little bit closer to 0, right? And so I think as we go on, these points, even though they're bouncing, they're settling down near 0. So we think the limit is 0. Well, let's see if we can apply this theorem to verify that. What if I took the limit as n goes to infinity of the absolute value of this sequence? Well, here's what the nice thing about the absolute value is that it kills the alternating part, but everything else will stay the same. So really you just get this, right? Because if n is even, then this is already 1 in the numerator anyway, and the absolute value doesn't do anything. But if n is odd, you get a -1 in the numerator, but the absolute value will turn that to a positive, right? So the absolute value kills the alternating part, and you just get this sequence here after doing the absolute value. And as n becomes large, you get 1 over very large numbers, which goes to 0. So what have we shown? We showed that the limit of the absolute value equals 0. Well, now we conclude, so therefore, by this theorem here, the limit of the sequence we want also goes to 0. And it's by this theorem. I'll say it's by the star theorem, right? Okay, see if you can try this one. Looking at the sequence, when n is 1, you get -1 over 1, which is -1. When n is 2, you get -1 squared, which is +1 over 2, which is 1/2. Then -1/3, +1/4. The next one I think would be -1/5, which is a little bit closer to 0. So we have this similar behavior happening, right, where it's bouncing back and forth, but looks to be settling at 0. So maybe we think the limit is again 0. Let's see if we can verify this. Go ahead and try this on your own first. Pause the video. But we're going to try to apply this theorem. So we're going to take the limit of the absolute value of the sequence. Well, once again, the absolute value kills the alternating part. As n becomes large, you get 1 over large numbers, which is close to 0. Oh, so we showed what we were supposed to show, right? We showed that the limit of the absolute value goes to 0. Therefore, by this star theorem, the limit as n goes to infinity of the original sequence, the one that we're trying to find the limit of, must be 0. Moving down here to the second half of the page, we have this theorem about continuity and convergence. It essentially says, in all intents and purposes, it essentially says that just like in Calc 1 in most cases, the limit can move inside of a function. So when we look here, because sine is what's known as a continuous function, if you remember the definition of that from Calc 1, then we can take the limit here and move it inside the sine function. And now apply what we know. So as n becomes large, pi over n is very, very close to 0, right? So this limit on the inside is 0. Oh, well, sine of 0 is 0, right? So go ahead and try the same thing here. We can move the limit inside the tangent function. Pause the video if you like to compute this limit. But you'll notice that the top is going to infinity, as is the bottom. And so we can actually apply L'Hopital's rule just on this inner limit here. And so we get the limit, n goes to infinity. Well, derivative of the top is 2 pi. Derivative of the bottom is 8. This is just a number, so it's the tangent of 2 pi over 8, which you may know as the tangent of pi over 4. Well, the tangent of pi over 4 is just 1. Really, all this theorem is doing is allowing us to move the limit inside of continuous functions. Okay, and now the final piece to this page is this example here, where you see here we have not only a factorial, but also this weird exponential function where the variable occurs in both the exponent and in the base. we can't really apply any kind of L'Hopital's argument to this, at least not with Calc 1 knowledge. So we need to use a different method here. We're going to compute the limit sort of by using what's known as like first principles. And the first observation I want to make is the following. So first, observe that an is positive for all n. Right? You just get positive number divided by positive number. So hopefully that's clear. But now let's start computing these. So a1 is going to be 1 factorial over 1 to the first. And now if you know what a factorial is, I mean 1 factorial is just 1, and 1 to the first is just 1. We'll get into what a factorial means in just a second. So a2 is going to be 2 factorial over 2 squared, right? Just plugging in 2 for n. Well, here's what a factorial is. You start with that number, and then keep multiplying by the next smallest integer until you get to 1. So 2 factorial is just 2 times 1. Now I'm going to write 2 squared as 2 times 2. And you'll notice that these leading 2's cancel, and I just get 1/2. Right? And you might be wondering why I left this as a fraction 1 over 1. We'll get to that in just a minute. Let's do a3. And maybe you can do this first by pausing the video. But you get 3 factorial over 3 cubed, which is 3 times 2 times 1 over 3 times 3 times 3. Notice the leading 3's cancel. So I get 2 over 3 times 1 over 3. And here's the key observation. 2/3 is less than 1. When I multiply a number, say for example 1/3, by a number that's less than 1, that's going to be less than the other number, right? So in this case, I'm multiplying 1/3 by a number less than 1. So my result is less than 1/3. Okay. Let's try a4. That's 4 factorial over 4 to the 4th. That's 4 times 3 times 2 times 1 over 4 times 4 times 4 times 4. Well, this is, after canceling the leading 4's, 3/4 times 2/4 times 1/4. I am multiplying 1/4 by a number less than 1, so this is less than 1/4. But now I'm multiplying that by another number less than 1. So the whole product is less than 1/4. Okay? So now if I were to say, can you tell me what a5 you think is going to be less than, hopefully you can see the pattern that once you get to 3, a3 is less than 1/3, a4 is less than 1/4, a5 is probably less than 1/5. And in general, an is going to be less than 1 over n. But now to pick up these first two cases, notice the following, that a1 is dead on equal to 1 over 1, and a2 is dead on equal to 1 over 2. So we can capture those first two cases by putting an or equal to symbol, right? And so now we have the following relationship here. So we have that for all n greater than or equal to 1, 0 less than an, that's this part right here, less than or equal to 1 over n, which we just found right here. And so by squeeze theorem, well, let's find out. As n becomes very, very large, 0 does not change, so I still get 0 over here. As n becomes very, very large, I also get 0 over here. So where do we think an has to go? Well, the limit as n goes to infinity of an must also go exactly to where the two outer parts are going. Since limit of 0 is 0, and limit 1 over n also equals 0. Right? Okay, so that's the end of this page. We'll, in the next video, do page 53, which is the next page of the notes, where we learn about what are known as geometric sequences.